Hi guys, George with Troglodyne here. I'm going to give you guys a overview of the technical part of my presentation I did to Houston PM last week. This is going to be accompanied by a more or less a term paper describing how all of the math and the algorithms got put together for the pairwise test execution program that I'm writing right now. I'll make sure to link the general description of the program in the description of this video and the link to the very in detail discussion of this that goes far into more detail than I'm ever going to be able to talk to on a video without boring you all to tears in the description of this video as well. So let's just get right into it. So when I started building this tool, as I mentioned in the other video, I didn't find what I needed on CPAN. I didn't find all those things. A lot of that is because these sort of rub up against some hard problems in computer science and in number theory and mathematics. But it turns out that sort of the way that you build your constraints as a program is almost always the way that you can find a way to weasel out from under the really hard problems. It reminds me sort of the tyranny of the rocket equation, which if you've never read a book called Ignition, it's really great. It's about, how we actually figured out how to make rocket fuel, get all the way up into space and all that stuff. But the long story short here is that we only got into space because we cheated. Okay. We decided to put a little rocket on a big rocket, and that's how we solved the problem. We just changed the constraints of the system and it worked. And it's the same sort of thing here. Just to get right into it, when we look at these groups of platforms here, you might notice something very particular about all of them. And none of them ever repeats an element in between each list, right? So this is a very realistic thing when you're actually building a system under test. You can't have a system which is, its operating system is also a CPU architecture. That just literally makes no sense, right? So that's one constraint that is literally going to save our lives here, because if this is not true, then we very quickly descend into, NP hard Ramsey theory hell, which is also known as the click problem. I can sort of refresh your memory here real quick, or tell you sort of what it's about in case you're not familiar. Basically, you might have seen, like I showed you here, that these are just lists of strings, right? Well, what does that have to do with number theory? I mean, they're numbers, right? Or graph theory, it's graphs, which is numbers, right? Well, it turns out you can cardinalize any string. You can just assign a number to it, and it's essentially equivalent to anything else. And so then any kind of combination you're going to build based off of these other sets or supersets you're going to build thereof are naturally going to correspond to vertices in a graph, right? So click theory is all about, well, how do I find out which vertices are the most associated and sort of build the clicks of, well, these are the vertices that are at least one distance away from each other. These are the ones that are two distance away from each other, yada, yada, yada. They don't share any other vertices, things like that. In particular, it turns out our problem is actually one of the anti-click problem, which is what are the ones that actually don't share any other vertices that they connect to, right? So this vertex doesn't connect to any other vertex that we've actually picked out of our bag, right? So it sort of results in this alternating pattern where we're not dealing with that. So just to jump into sort of why this is the situation, it's because I chose to not do a straightforward combination, which is essentially going to be far too many configurations to test. When you're doing in-wise instead of pairwise, which is just a two-dimensional thing, we want to go up to n dimensions. As you can see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 dimensions here, right? That is going to essentially just be a standard R combination, which is going to result in thousands, tens of thousands. Point is, way too many configurations for you to actually test either timely or in a cost-efficient manner when you have a situation in an organization where you have multiple commits coming in, even in an hour, right? Where it's just by the time you've tied your shoelaces and you're ready to test, you've already got a new commit that's come in that's invalidated any previous results. You really got to snap, get going really fast. So the other half of this problem is that, so we've got to build these anti-clicks, right? Essentially, these are bins that we're going to stuff tests into, okay? And so when we've got these bins, how do we want to pack the tests into the bins? Well, obviously, since we want to get test execution done in as little time as possible, we probably want to fairly pack the bins where it's essentially the same number of test files in each bin. That's an oversimplification of the matter, but you'll find out we don't really have any good options other than to take this sort of oversimplification. And I'll get into why that is later. But we then need to make sure that we handle edge cases like, well, what if we have less tests than bins? In that case, you're going to want to do something like repeat some of the tests so that you can get these combinations churned through faster, because the whole idea is that if I generate a minimal set of combinations, which I would call optimal, for example, in this set would be 8 combinations per iteration, which is essentially bounded by our largest set, which is browsers here. So that would be resultant in, I don't cover every combination every time. I do cover a manageable chunk every time. And the idea is that as these commits are coming through that we need to run tests on, over time, with enough iterations, we're going to cover a large enough subset of our entire combination space that it's going to essentially smoke out everything that's actually important. Generally, when you get 80% coverage of a configuration space, you've probably found most of what there is to find. You don't really have to go exhaustive on this stuff for most problem spaces. Sometimes you do, but most times you don't. And certainly not for the use case of I'm just doing smoke testing on commits that are coming through, right? But I do want to have more rigor than just, I'm only running one smoke.t or something like that, right? Generally, when you're going to do something like a release or something big, that's when you're going to do your full combination run. That's when you're going to do your more extended validation if it turns out that your ability to make updates to the software in the field are lacking because, there's various reasons that can happen. It's flashed onto an ISA, something like that. Anyways, so the other constraint here that's worth mentioning is that none of the elements in any of these sets is repeated. So it wouldn't make any sense to have CentOS twice in the operating system list, right? So if that also happened, then we would be yet again into NP hardland. So we don't want either of those, and thankfully these constraints are realistic, which makes us very happy. And the point to all this constraint discussion is that rather than having to use a hard approximation algorithm, we can just use the Chinese remainder because this is actually the weak pigeonhole principle, which is a fairly straightforward concept in combinatorics. In fact, my combinatorics textbook is around here somewhere, but it's the first chapter. So anyways, the other thing you'll notice here about our little configuration hash that I built here, in the real world, you're going to have some pieces of software which are incompatible with other pieces of software. For example, CentOS might not run Internet Explorer, right? Or OS X doesn't have a 32-bit operating system anymore, right? You can go as detailed as you want with your configuration groups and so forth, but the point is we're going to have some mechanism to have our users describe what is an invalid configuration. And thankfully, due to those two constraints that I discussed earlier, we can actually have this be a very simple data structure, which means that our algorithm down the road is actually going to be really simple for dealing with it as well. You can see basically all we do is we say, well, here's the thing, and we're going to just dump a bag of stuff that can be from any of these lists. It's just like this could be from any of these lists, and just move on and call it a day. So let's get right into the code. So this is the test, and you can see, just as an idea, here's our sort of test data set that I'm going to show you sort of the results of profiling later. I figured 100 million tests was probably kind of a worst case situation. I think I've heard maybe of 2 firms that had more than 100,000 tests, 100 million tests to execute. And in that case, pretty much all failures were ignored because it was just a fire hose. But I'm going to support it. And in fact, I'm going to support it really good. We're going to have great performance at the end of this. So yeah, here's our algorithm. So to grab our clicks, what we need to do is we need to first process our input data, which, as I mentioned here, is all this stuff. And then we're going to make sure that we shuffle the elements of each of these platform groups. So CentOS, Ubuntu, Windows OS X, or whatever this stuff is, we're going to randomize the order of this such that we can actually satisfy that goal of eventual consistency across iterations of commits and test runs, right? Because otherwise you would just get the same configurations every single time, and that wouldn't provide any value. So we get that shuffled up, and then what we need to do is we need to do our pigeonhole principle sort of accounting. We need to go ahead and grab what is the longest group, and that's just sort it and pop the top one off. And then you need to grab the length of that longest configuration group, because all this does is tell me which one it is, not how long it is. And then I need to know how many tests I actually have that are being brought in to split up amongst these different groups. You'll note that this doesn't actually solve the problem of apportioning them amongst multiple systems under test, which all satisfy one particular configuration. That's a great deal simpler problem, and it's just fair item allocation, which we'll go into with bin covering here. As you can see, it's essentially just a fair division, but colored by the fact that we use float division here in Perl, and we don't have exact numbers. We don't have any of those things. So we're going to have to do a couple of mitigants to make sure that we actually have exact results, despite all the rounding errors and all the stuff that float math implies. So we're going to take a remainder, and we're going to grab essentially the fair division and go from there. We're going to also add a little bit of code down below to make sure that we at least get one for every platform to satisfy exactly this case of you have more bins than tests to execute, because then you floor a float that's below 1, you're always going to get 0, so you're going to have to clamp the value to 1. Anyway, so what we do is we go and say, okay, for every we're going to just go and build every single one of these new sets with an element from the longest set, right? So we're sorting it again to make sure that we have the longest set right at the front there, and we're making sure to have our iterator go only as long as our longest set. And here's where we're using Chinese remainder. So we are essentially going to say, I'm going to pick out whichever element of the list is the current index modulo however long our existing list is. So that way it'll wrap around if this list is smaller than the longest list, which is pretty much guaranteed. And so then, as we go through them, and since we randomize them, this will always guarantee that we pick one of everything else. So the next thing to mention is that we need to handle this invalidity, right? So we're going to use this combination valid function, which I'll go over later, and we're going to reject anything that is invalid, and we're going to do basically re-roll the dice by incrementing our index by 1 temporarily in this block, and then we're going to say, okay, well, let's go and see if this one is actually valid, and if it is valid, then we break out of the loop and we just push it right on. And then if it turns out we roll all the way back to our original starting position here, which is our last right here, then we're going to say, well, there's nothing valid that's possible with this configuration group because, and let me show you here. So, for example, it's possible that you have, say, an operating system which is incompatible with literally everything. So, for example, it might be that Windows supports no message queues. This is not true, but suppose it was. And we need to actually support that situation because it's very likely to happen in reality where you have some kind of companion software that is just not supported on one of the supported operating systems. And so then we just push this, set of this partial combination to a temporary array until we get all the way to a fully fleshed out combination. And then we need to fill the bins, right? So you can see this is where we're doing all of that clamping and correction for rounding error and all that stuff. So this is essentially all it is. You're taking however many it is to take, which, again, in some cases will literally be 0. And so what we're doing is this OR is clamping it to 1, making sure that it is at least that. And then otherwise we're doing the remainder ANDed with 1 because, again, the remainder can also be 0. So that'll make sure that we choose at least the number of tests we actually have. It will also mean that we repeat some of them if it turns out we have less tests than bins. But this is actually a good thing in that it'll mean that we execute over these iterations. We actually churn through all of the iterations, all of the configurations we need to get full coverage a good deal faster than we would otherwise. Now, I'm not sure how you're going to feel about having less tests written than combinations you support. That doesn't sound like it's going to be exactly a sound practice for your software quality. But hey, a good solution supports even the craziest configuration. That is within reason, right? Yeah. I contain multitudes. I can, be a little crazy if I need to. That's how mathematics works, right? We need an optimal solution. Anyways, so as you can see here, this is the mechanism by which I'm actually doing this repeating tests, and this offset being added to is essentially just to make sure that we are adding up. We're making sure that the tests we want to take from our test array, we're telling, here's the offset you need to grab them from, and here's the number of tests you need to grab them from. Rather than splicing out of the test array, we're just giving these offsets and indexes, because if we actually do the splice on 100 million test array, that's going to take a really long time, especially in even larger numbers. It's very quick to exhaust memory. But by doing lazy execution like this, which we can actually consider a really realistic situation, because in the context we're going to be running this tool, it's going to be just one of these nodes that satisfies being a system under test for these configurations. It's only going to need to know which tests it has to execute, right? So that means that our performance is going to be bounded to however long it takes to actually get up to our offset plus our index, right? So that's a great deal less performance problem, except for the last one in the list, right? So that means we'll have less total execution time, but there's only so much we can do, right? Without being able to figure out how to jump ahead. But when you think about how do I actually jump ahead in a list that I don't necessarily know ahead of time what all it contains, because suppose it's like a file glob or a regex used to find all of these list tests. Well, that actually gets into the realm of yet another NP hard problem, which I'm trying to remember what it's called. It's sort of got a lot to do with like De Vries problem, and De Morgan's problems. It's parity problem. That's what it's called, parity problem. So it's essentially, like I said, a lot of people are like, well, how does these number things actually associate to that? Well, the parity problem is essentially like, how can you determine what is even and odd in multiple dimensions? And it's sort of the same problem here with regard to, well, you're either going to match a regex or you're not. So that sort of is a lot like even or odd. You're either even or you're odd, right? So you're going to match or you're going to not. So those problems are actually pretty undecidable, and it's a sort of an open question whether that can be solved in a closed form way. I suspect it'll probably require a generalized solution to the Goldbach conjecture or something like that to actually understand the problem well enough to build an algorithm that can do that. Anyways, so the only thing that is worth mentioning here is that the way that we're solving this rounding error here with this remainder is essentially, suppose you've got, so here's our combinations, right? So we've got all 8 of these different combinations. And suppose I have a remainder of 8 from a group of like 53 tests and 40 bins or something like that. It's not a realistic number, but just bear with me. So what we would do is we would chop off 1 from that remainder for each bin and just hand it out, right? That'll do the trick. So that's essentially all this is doing. We are adding the remainder, ANDed with 1, of course, to yet again clamp it to 1, and then making sure that we go ahead and slice off a piece after we've added, and then move on in the algorithm. So, all right, let's move on down to the combination valid algorithm. So I mentioned this earlier, and so what we're going to do is we're going to load up the incompatibilities, and we're going to then iterate over the different incompatibilities, and we're going to say, if it looks like we happen to be an array which has both my incompatibility and one of my incompatibilities in it, then we're going to return false. It's pretty simple, right? As you can see, it's just if this array returned by this double grep is greater than 1, then that means the combination that we see, like say this, happens to contain both something with an incompatibility and one of its incompatibilities, and you just move right along. So I think this is probably a good time to mention sort of the profiling aspects we got with a lot of this. Let me actually load up the flame graph if I've got it. Yeah, so here we go. As you can see, this is how long it actually takes to implement the clicks algorithm. It is 11 milliseconds. So, that's obviously a pretty good performance for 100 million tests, right? But, it took 3.5 seconds to generate a sequence with 100 million integers in it, which we're using sort of as our stand-in for 100 million tests. I'm sure doing a glob that results in 100 million results or a regex that results in 100 million results is going to be a great deal worse. But hopefully no one is crazy enough to have, 100 million tests. 100 million assertions inside of, lesser tests. Yeah, that makes more sense. But in this case, you'd probably fill up the disk inodes long before you even think about testing. Anyways, so we've got another algorithm here called combine, which is, since the name of this tool is actually Pairwise, I made sure to implement actual NYs, which is just a multi-dimensional combination, right? And so that algorithm itself took 1.5 seconds, most of which was sitting in this combination valid function. And in fact, it used to take 3 seconds, again, most of it which was in this combination valid function. And the way I had to optimize it was that first I was allocating the results of this grep to a variable, which just removing that and returning directly shaved 200 milliseconds off of it. So, assignment in tight loop, you need to avoid it. And then the other thing was I was doing a quick guard on, you can see there's a guard here to check that the element is defined, which as I mentioned, you might have some of these incompatibilities leave a sort of blank spot in the set. I may not have mentioned that, but the point is that that is a possibility because of these incompatibilities. Because we're not rejecting them out of hand, as you can see here. Yeah, so as you can see, we're not rejecting them out of hand. What we're doing is instead we're just iteratively trying to get the one, and we just give up here if it turns out we can't find any way to satisfy it, and we just move on. Now, what we could do, on the other hand, is we could do back propagation and re-roll iteratively back, so for example, if this is the third element in our prospective like 7-element array, like say we got Dillo MariaDB exchange, and it turns out CentOS is the thing that's incompatible with that. Well, what we could do is we could iteratively step back and then re-roll until we get something that we can actually move forward for. But that's a lot more work computationally. And it turns out that if you instead just accept a little bit of slop, where say, for example, instead of when you see undef instead where CentOS is or nothing there, you can just assume, well, I'll just use any old OS and it'll work fine. That will actually speed up execution a great deal. And yeah, it's a little bit of slop in the production process, but it also speeds up the algorithm significantly. And it's probably worth it at the end of the day. Anyways, so like I mentioned, I also had a guard here that was checking that the ref for the actual incompatibilities was of the right type. But it turns out doing ref 100 million times takes a second. So had to get rid of that. Define, on the other hand, doesn't take nearly as much time. I turned off warnings and got rid of it, because that's the reason it's there, is to suppress warnings. And it didn't shave any appreciable time. So define is actually pretty efficient. Anyways, so what we have left is to go over the actual in-dimensional combination algorithm. So it's essentially going to be very similar to the procedure for the last one, except we're going to generate more with slight differences in the algorithm. So what we're going to do is we are going to find out how many bins we're going to end up with totally, which is going to be the product of the length of all of these different combination groups. So for example, this would be 4 times 2 times 8 times 5 times 4 times 5 times 2 times 3. As you can imagine, that's a lot, right? So we're then going to grab the number of tests, and then we're going to do the same exact remainder trick that we did last time to deal with rounding errors and yada, yada, yada. And so what we're going to do is we're going to build an iterator. And we're going to push partials to this iterator and then go ahead and just keep pushing new combinations onto it, right? So the best example I can sort of show you here is with the data, right? So I'm going to start out with, say, Firefox, right? And so then I'm going to encounter the CPU architectures as the next group I want to come through. So I'm going to push to this iterator Firefox 32-bit and Firefox 64-bit. And then I'm going to say, okay, well, I'm going to treat this new partial I have the same as I treated browser in the first iteration. And I'm going to go ahead and combine it with operating systems. So now I'm going to have Firefox 32-bit combined with CentOS, Firefox 32-bit with Ubuntu, on, and Firefox 64-bit with the same. And so we're going to build this iterator containing this ever increasingly large set of partials until we run out of stuff to actually add to these partials, and then we're done. This is obviously a pretty greedy algorithm. So, it takes a non-trivial amount of RAM to actually do this test for 100 million tests and so forth. So, be aware of that, but I don't think it's going to kill anybody's computer or even be so bad that I can't just include it inside of the distribution test suite. But it does take, a second to execute, so we might just keep it as author testing because of that. Anyways, so I don't think there's anything else really of consequence to mention here. We're basically doing the exact same trick to deal with valid combinations, but with one minor foible here. Instead of there's no element there, what we're going to have is undef, but we're going to need to be able to have whatever parse of this treat both situations as essentially the same. What I'll likely do is I'll use grep to just filter those out on the back end, because that just won't take any time. Anyways, that's essentially the long and short of how the algorithm actually works. I can go over probably, again, filling the bins from a theoretical point here. It's what's called the fair item allocation problem. And this has some unexamined pieces that are worth mentioning. Number one, it's not exactly fair, because this assumption that every test we're putting inside of these bins is actually equal is not really true. Every test is going to take a slightly different amount of time to execute, and the time it takes to execute is not going to be consistent across iterations as changes to both the tests and the system under test actually come in, right? So there's no real way for you to predict any of that stuff. So you might as well just take it as a given and give up on it. Again, this is going to introduce slop into the production process, but it's slop we can't do anything about. It's essentially an undecidable problem, so we're just going to have to deal with it. And let's see, any other things that we have here? I'm looking at my little essay that I've written here. Oh, there's another significant complication. If all the items that we put into the bin are indivisible, then that simplifies things significantly. Thankfully, we can sort of push that on to the tester and the test authors, because if they wanted to split up their tests more than they already were, they would be doing it, right? Because it would make it to where, for example, when you run prove with multiple processes, it would execute quicker, right? Because there's some test execution time at which it doesn't make sense to split it up, because the overhead for forking is just going to overwhelm the few milliseconds that you save, right? So anyways, the last thing that I want to mention here is sort of the core takeaways I got from building stuff in the way I did while I was writing all of this algorithm. In fact, this sort of started as a centralized approach using Elasticsearch to be essentially a test management system, but I realized that all that's a lot of work, and it doesn't allow sort of the organic growth that things generally tend to use. And there's a reason Git succeeded. It's because it was viral, man. And this being spread through the same mechanism, I think, is actually going to spread some of these test management techniques to development organizations where, at least in the automated sense, they've just not had a lot of penetration, which there's no reason why organizations can't benefit from these sorts of optimizations to their production process. And so, to go meta on you for a second, I was thinking about my own production process. Writing this was basically, I was writing this big term paper basically about how it actually works, how the math works, making sure that we're valid, making sure that we have a very solid, place to stand on when we're building this. That actually challenged a lot of my assumptions that I had in the original versions of these algorithms. In fact, they were so buggy that I'm almost embarrassed I have it on CPAN. So this is actually very much better code, just because I actually went in and did the right thing that I should have done in the first place and trusted my math education and went from first principles, and then went in and tested it, made sure that these hypotheses were correct, that these ideas worked. And it turned out that, this made it all come together in about 3 days in preparation for Houston.pm. So I was very happy. It was a very fast and a very high quality and high output production process. This sort of reminds me of how things actually go in modern programming organizations and modern bureaucratic organizations. Is a lot of times when you're developing something, you get technical debt, which is essentially because what you were developing didn't actually understand the problem when you were going into it, right? And so what you built was actually suboptimal, and you sort of just had to shoehorn it in at the last minute to actually meet customer needs, right? And so I think this approach makes it to where you're thinking a great deal more about, well, what are the constraints? I need to know the constraints, which are very close, but not entirely equal to user acceptance criteria. And that gets things on a much, much more solid ground. And it also forces you to, when you're dealing with algorithms in particular, you got to profile this stuff, because you can have the best algorithm in the world and have it completely kneecapped by just using a bad language feature, or putting in a guard, for example, where you just don't need it, you know. So that sort of stuff really helped out, and it reminds me, at the end of the day, we all operate under what's called bounded rationality, right? Where we have limited information, we have limited time, we can only do so much with what we have. And so, how do we maximize getting what we can get out of what we have, the limited information we have? You know, I'm just a small developer, so I don't have a lot of access to customers readily available to, you know, perform Mingala science on to check out all of my assumptions are valid. But what I do have, on the other hand, is the ability to look through the past. I have the ability to look at all these mathematical things that have come before me. I have the ability to do all these things if I just do the research. And that really helps out a lot for understanding, well, what's possible, you know, and then from what's possible, you can refine those constraints. And while I was refining those constraints to make the problem more possible, I actually saw several opportunities, like, for example, including tests in these situations where we have less tests than bins. I saw opportunities we could actually provide extra value for the user that I wouldn't have simply encountered at all had I not been thinking on this level. And so that's really about all I got for it. And I'm very happy with the approach. And hopefully this will result in some very good content for all of you guys to chew on if you're interested in these sorts of subjects going forward. Because I like this model. I'm going to keep doing it. All right. Well, I will say goodbye. Have a good one, guys.